Welcome to this lecture. In the previous lecture, we have just started about the mechanics of solids in MEMS and the NEMS devices, where we have studied about the rigid body and deformable bodies, and in deformable body we have discussed about the bar. In that, it can contract or it can expand in only axial direction. Now today we will discuss about a beam in which we are applying a transverse force that is in parallel with the cross section area of the bar. So instead of increasing the length in axial direction, it will bend. So this is known as beam. We can see a short straight segment with the constant beam movement, bending movement before let this is the straight beam, and the length is L we are taking, and the total width C we are taking, and or H we can take. And after bending, this is the situation where it will make a radius, it will make a curvature of radius rho, and this angle is theta. It's making it the center point. We can see there is a natural axis, there is axis in this. So above this axis, this material of this beam will be contract, and below that it will expand. Okay, so there is a line in between these two at the approx center of this beam. At that point there is neither contraction nor elongation. So that axis will be known as natural axis. From the diagram we can see calculate the axial strain, that is the del L by L, change in length by original length. So we can see from this equation that the initial length, that is theta into rho theta, we can take the initial length. This is the initial length rho theta, and after increasing, and the length will be this at this position, this position length will be decreased. So we can say that new length is lesser than previous one. So we can write the length after this contraction, that will be rho into L minus X. Okay, so this is the rho minus Y into theta minus rho theta upon theta. This is the initial length, and this is rho minus Y into theta. Okay, so why rho minus phi? Because we can see from this diagram, the rho is the distance of the center point from the natural axis, and we are taking an imaginary axis, imaginary line, that is that has a distance of y from this natural axis. This dotted line is the natural axis, so it has the distance of y from the natural axis. So we are writing for this line, we can write epsilon x, that is rho in minus y, this rho minus y into theta minus rho theta upon rho theta. So this is the new length, rho minus y into theta minus rho theta upon theta. After calculation we will get minus y upon rho. The maximum value of this y will give the maximum strain, that is epsilon max equals to C by rho, because the total length of this bar, the thickness of this bar is 2C, so half of this one is C. So we can write epsilon max is equal to C by rho. Then the strain, this is, we are taking the strain along the vertical axis of the beam, we can take right as minus, we can replace this rho with y by epsilon, minus y by epsilon. So we can write y by C into epsilon, y epsilon max into C. So we can calculate, or what we have done, we have just replaced this rho by C by epsilon max. So we have written here epsilon x is equal to minus y upon C by epsilon x. So we can write this y into epsilon x, epsilon max upon C. This is value of the vertical cross section of the beam, strain along vertical cross section of the beam. So then we move forward further. Then the stress, this is the strain, and stress we can calculate using the Hooke's law. What is sigma x equal to E into epsilon x. E is a Young modulus, so minus E into this y epsilon max upon C. So E y epsilon max upon C, or again E into epsilon x max, we can write this quantity as sigma max. So we can write minus y into sigma max upon C. So this is the value of sigma x equal to y sigma max upon C. Here epsilon x equal to y epsilon max upon C. Similarly this one, or we can write again in place of, if we are writing this C, we can be changed with rho. So we can write y into epsilon max y into E upon rho, we can write. So you can just try, you can just replace the C with epsilon max upon rho. So epsilon max upon C, you can write epsilon max upon C, so that is 1 by rho. So 1 by rho we can write this one. Okay, so in this equation epsilon max upon C you can write 1 upon rho, so minus E into y upon rho you can write. Next is the location of the natural axis. We have already discussed natural axis, that over which there will be contraction, or below which there will be elongation, but at that point there will be no contraction, no elongation. So zero effect will be there. So in this diagram we can see this is the rectangular beam where the width is W and height is C, we can take, and or H we can take. So this is the center line. At this point, above this one there is a contraction, and below this there is elongation. So this is the sigma x. So sigma x is negative for below, above this one, and below this one sigma x is positive. So at this point when sigma x is 0, that is the point where we can say this is a natural axis. So how we can calculate it? For calculating the natural axis pure bending, equilibrium, we can take the equilibrium of the axial forces, the total force at this axis, that will be 0. So fx in summation of fx is equal to 0. What is fx? That is sigma x upon dA, sigma x into dA, because sigma x strain stress, that is f upon a. This is f upon a. So we can write f equal to sigma x into dA. So replacing the sigma x again, sigma x value, we can write y into sigma max upon C multiply by W into dc dy, because the W is, this is fixed, only this length we are just moving from 0 center point to above. So we can write W into dy. So after that we can, this is a constant, sigma max upon C, W is a constant. So we can change minus sigma max into W upon C, integration of only y dy. These are the constant value. This is, it means if this value is 0, y dy is equal to 0. So this expression will define this is natural axis. Y dy is equal to 0. For calculating the curvature in the pure bending, how we can calculate the curvature? From equation first, which is there, this is equation epsilon x equal to minus y upon rho. So we can write this is natural axis. Then the curvature of in pure bending is related to internal bending moment m. What is the formula for internal bending moment? M is equal to some integration of y sigma x into dA. This is the value of m, y sigma x into dA, momentum, internal bending moment. So y into sigma is equal to sigma max upon C, y sigma max upon C. So sigma max upon C is here, and y square dA, it will come like this. So we can write this equation, that this is the inertia moment. We can write it as an inertia moment. So we can write m is equal to minus sigma max upon c into I. This is area inertia moment of inertia, that is y square dA, integration of y square dA. So we can write this equation again. Sigma max equals to cm by I minus cm upon I. Then sigma max, instead of sigma max we can write sigma x at any point from the center natural axis we can write. So when we are just changing sigma max to sigma x, we can write, instead of c we can write it as y. So minus ym upon I we can write. This is the physical property, and this I is for cross section area of the beam. So from previous equation first we have written already, that is sigma max equal to c by rho. So you can write 1 upon rho is equal to epsilon max upon c. Epsilon max is equal to sigma max upon EC, we have written by Hooke's law. So from equation D, that is what is equation D? Equation D is this one. This is equation D. Sigma max equal to minus Cm upon I. So we can write this one from equation D. 1 upon rho is equal to sigma max value. We can put Cm upon I into 1 upon EC. This is 1 upon EC into sigma max, meaning minus Cm upon I. So we can write m upon E I. M upon E into I. So this is the equation that is called the Euler-Bernoulli theorem for bending of beam. This is Euler-Bernoulli theorem for bending of beam. This is the relation between bending moment, internal moment, and this curvature rho. In the next lecture we will discuss about some more parameters for this bending beam in the pure bending. Till then, thank you.